Hi everyone, this is our continuation on the discussion of ionic bond formation, and right now we are on our third learning target, which is to represent ionic bond formation through Lewis electron dot structures or LEDs. Okay, so we ended up with this slide detailing an example of lithium and fluorine and how does a bond form, an ionic bond form between these two atoms. We mentioned that there are uh, different ways, three ways. One is through electron configuration, another is orbital diagram, and the third one is through LEDs. All right. So, as a review, electrons or atoms tend to gain or lose electrons in order to attain the configuration of a noble gas, okay, until their valence shell contains 8 electrons, especially for the period 2 elements. But for the smaller atoms, for example, like sodium and helium or hydrogen, then they just need to form a duet, not completely an octet. Okay, and there are a few rules also for writing the electron configurations of ions. Okay, so for group 1A, group 2A, metals and aluminum, so generally metals, they lose electrons until a noble gas configuration is reached. So for nonmetals, they gain electrons until a noble gas configuration is reached, okay, meaning they have 8 valence electrons. Now another set is for transition and post-transition metals, so they are quite an exception because of the presence of the D block, but generally they in terms of the S and the P, the goal is still the same. Okay, so more than one ion is often possible. So for example, Fe or iron can form Fe2 plus and Fe3 plus. Okay, so what happens there is transition metals lose their S sublevel electrons before their D electrons or the electrons in the D block. So that's why we have the following charges. Or ions, Fe2 plus, Fe3 plus, so zinc, copper, and copper 2 plus. Now for post-transition metals, meaning those metals that may be falling under the P block, but they are still uh, considered to be metals. So for example, tin and lead, okay, they lose their P sublevel electrons, then their S electrons. All right. So in terms of electron dot structure, so this was actually developed by Gilbert Newton Lewis, okay, wherein he represented valence electrons using dots, and the element symbol represents the nucleus and inner electrons. So again, the symbol of the element is surrounded by valence electrons, and then this is used to represent bond formation. Now, for representative elements or for those belonging to group A, okay, in the periodic table, the group number is equal to the number of valence electrons, such that it will be easy for us to draw the LEDs. Now, if you've noticed here, those belonging to group 1A, so for example, lithium, sodium, potassium, so on, they only have one valence electron. While for group 2A, you have two valence electrons, okay, and then it just follows, okay? It's just very easy. You just have to look at the group number before the letter A and then write your electrons, okay, as if it were parts or along the sides of a square. Now take note that they must be beside each other and not one on top, okay, such that it will really be forming later on a certain square. So just like here, neon. So two electrons for each side. And this represents a full octet, okay, 1, 2, 3, 4, 5, 6, 7, and 8. So that is how you draw the Lewis electron dot symbols for elements in periods 2 and 3. Right? Now we are going to go through a few examples. Okay, we are going to illustrate the ionic bond formation for a few elements, but let me just transfer to the Word document. Okay, then let's use this. Okay, so for example, we are asked to draw the ionic bond formation, represent the ionic bond formation of between potassium K and the chlorine atom. Okay, so K and Cl. So if you notice, K belongs to group 1, so it is in here. Therefore, it has one valence electron. So one valence electron for potassium, you can place that one valence electron anywhere. Okay, and then so let's redo one valence electron there, and then if you add an atom of Cl, okay, how many valence electrons does Cl have? So it is under group 7, therefore it has 7 valence electrons. So in here we draw 7 dots around Cl. So 1, 2, 3, 4, 5, 6, and then 7. Okay, so that is our LEDS for Cl. So in representing ionic bond formation, we usually represent the transfer using arrows. So what happens here is that one valence electron of potassium becomes or transferred to the Cl atom, okay, and becomes its new electron, such that you will end up with, so this is now the result, a potassium ion which has a full shell already, K plus. Do not forget the charge, okay? And then we represent it using and we represent that it's in ionic form already using a bracket. And then the Cl atom, which has a complete set of 8 valence electrons already. So Cl, okay, 1, 2, 3, 4, 5, 6, and then 7, and 8. Now, since you have an additional valence electron, so you are one greater, you have a net charge of -1 due to that additional electron. So that's why we denote it with -1 or just minus. Okay, so if it's 1, no need to write 1 as a coefficient. All right, so that is now how we represent K and Cl. Now, what if we are asked to do, uh, for example, magnesium, Mg, and bromine, Br. Okay, so the ionic bond formation between magnesium and bromine. All right, so if you try to look at your periodic table, magnesium belongs to group number 2, 2A. So how many electrons does magnesium have? There must be, okay, there must be 2 valence electrons. So if you draw, you write the symbol for magnesium, Mg, okay, and then there are 2 valence electrons for magnesium, and then you have Br. How many valence electrons are there for bromine? So it belongs to group number 7, 7A, right? So it's in here, so there must be 7 valence electrons for bromine. This is 1, 2, 3, 4, 5, 6, and then 7. Okay, so what happens here is all the electrons of the metal must be donated or must be transferred. Okay, magnesium wants to get rid of its valence electrons. So bromine can accommodate one additional electron. So let's say we transfer magnesium, the electron from magnesium, into this side of bromine. Okay, so we use arrows to represent the transfer, and then there's a new electron for bromine. Okay, you notice that this bromine atom already has a complete octet. Okay, but this magnesium has one remaining valence electron. So this is what we call a free radical. Okay, it has one valence electron, one lonely electron, and this species is very reactive. Okay, so in order for it to become stable, it must be able to donate this one valence electron. And what do we do? So we add another bromine atom, okay, and then we know that it's originally having 7 valence electrons, and that extra electron from magnesium goes now, disregard this one line, goes now to, let's erase. This one valence electron from magnesium goes now to bromine, right? So again, originally there was a dot here representing 7 valence electrons. So if that electron from magnesium transfers to bromine, then you have it there. Okay, so in writing the chemical formula, okay, in writing the result, we actually have the ion, the magnesium ion, Mg, 2 plus or plus 2, either way. So if it's no longer 1, you really need to write the number. Okay, so plus 2 meaning it lost 2 electrons in order for it to become stable. Okay, and then bracket. And then since there are two bromine atoms or two bromine atoms where the electrons transferred to, we also write 2 and then Br. So we place the ion, the bromine ion, inside the bracket. Okay, since we already write 2 here, then we need only to draw the LEDS of one bromine atom inside the bracket. Okay, just like in math ba. So bromine Br there, and then there is one new electron. We represent it using X, and the charge there is minus. All right, so that gives us that Mg plus 2, 2Br ions. Okay, now I'd like you to take note at the charges. So this one has a charge of, let's say, we change the color. Magnesium has a charge of plus 2, and bromine has a charge of negative 1. Since there are 2 bromine ions here, then we place it negative 2. Okay, so if you get the whole charge, or the total charge of these, so plus 2 plus minus 2, you get a net charge of 0. That means the resulting compound is electrically neutral. Okay, meaning that it has 0 charge. So the same thing happens here in KCl. So this is plus 1, K is plus 1, and then Cl is negative 1. So plus 1 plus negative 1 is equal to 0. So meaning to say, the resulting ionic compounds are electrically neutral, meaning they cannot conduct electricity unless they are molten. But that's for you to figure out later on in the next virtual lab. Alright? So, if you get now the chemical formula in the first example, you actually have one atom of K and another atom of Cl. Okay? So that's KCl. That's potassium chloride. Okay, 1:1 ratio. However, if you place it here, magnesium, so Mg, Sorry. So if you place it here, magnesium, this is Mg, and then there are two ions of bromine, so that's basically Br sub 2. Alright, magnesium bromide, MgBr2. Okay, now I'll give you a shortcut. Okay, and I think you've already learned this, but just a review. So if you look at the component ions forming magnesium bromide, that is Mg plus 2 plus Br minus. What happens here is that you just crisscross and disregard the sign. So meaning the exponent of the metal becomes the subscript of the non-metal, and the superscript of the non-metal becomes the subscript of the metal. Okay, so and then if it's one, if it is one, no need to write one. Okay, so here, so MgBr2, the result is Mg. Since it's negative 1, so disregard the sign. Again, crisscross, disregard the sign. So this is Mg Br sub 2. So the 2 comes from the superscript of, or from the charge of magnesium. Alright? So that's basically how we represent ionic bond formation using LEDs, and in doing so we were able to get the chemical formula, okay, and the charges. Alright? So in the next few exercises, you will be doing something like this, okay, just as a practice, okay, and an analysis also. Alright, so that's it maybe for this lecture, and you may take your break, grab a cup of coffee, or have your snacks.